What's up guys, and welcome back to another video right here in the Calculus Stories channel. So, in this video, we'll go ahead and be looking at the very same example that we saw in the factor theorem. The only difference is that we'll go ahead and be using a different theorem, which is known as the remainder theorem, to answer the same question. Now, I'll go ahead and get into it later on, why this theorem is much more powerful than the factor theorem, but for right now, let's go ahead and consider the definition. So, if x minus a, which is the factor in question, is a true factor of f of x, then the remainder of the operation f of x divided by x minus a must be equal to 0. So in this case, again, f of x is equal to x cubed minus 6x squared plus 11x minus 6. And the x minus a factor in question is, again, the x minus 3 factor. Now again, the remainder theorem mentions the operation of f of x divided by x minus a, and if we want to prove that x minus 3 is a true factor, then we should expect the remainder to be 0 once we carry out this operation of f of x divided by x minus a. Now, you don't simply use this theorem to go ahead and show that the given factor is a true factor of a function f of x. You can just use the factor theorem for that and have a much easier time figuring that question out. The hidden property behind the remainder theorem that makes this theorem so powerful is described in the following sentence. So, the powerful property we can use from the remainder theorem is the fact that the function f of x can be rewritten in terms of its divisor and quotient by using the following equation. F of x is equal to the divisor, the thing that does the dividing, times the quotient. Now again, we can only use this if the remainder theorem holds true. So we'll go ahead and use the remainder theorem on our example. We'll divide f of x by the factor in question, which is x minus 3. If it is equal to 0, then not only have we shown that x minus 3 is a true factor of f of x, but we'll be able to rewrite our polynomial function f of x in terms of its divisor and its quotient. Right, so let's go ahead and jump right in. So remember from long division that whatever is on the top or in the numerator goes within the division house. So on the inside, we're going to have x cubed minus 6x squared plus 11x minus 6. And the denominator, or in other words, the divisor, goes on the outside. In this case, our x minus 3 expression. Now, when carrying out this polynomial long division, the most important element out of this entire expression is the lead term on the divisor. In this case, our x. To go ahead and come up with the appropriate answer for this division, all we have to think about is what is missing from x that's preventing it from being x cubed. And once we start this process, then we just keep applying it over and over and over again until our remainder is 0. So now that we know this, let's go ahead and try and see if we can go ahead and carry out the operation. So again, the question, what's preventing x from becoming x cubed? Or in other words, what do we have to multiply x by to get to x cubed? In this case, what's missing from x to get to x cubed are 2 more x's, or in other words, x squared. And so when you multiply x times x squared, we get x cubed. And just remember that you have to multiply -3 by this x squared term as well. And when you multiply -3 times x squared, we get -3x squared. We put this expression around parentheses, and we just simply put a minus on the outside. So when we subtract x cubed with minus x cubed, we get 0. When we combine -6x squared with positive 3x squared, we get -3x squared. We bring the next term down, which in this case is 11x. And before we go up top again, let's go ahead and clean this up, and we'll repeat the process. Right, so the 0 is just unnecessary, and so we'll just go ahead and bring everything else down, and we'll write negative 3x squared plus 11x, and we repeat the process. And so again, the question that you have to ask yourself is, what's missing from x to get to negative 3x squared? Or in other words, what do I have to multiply x by to get to negative 3x squared? In this case, I'm missing a minus 3 and one more x. So when I multiply x times negative 3x, I get negative 3x squared. And when I multiply negative 3 times negative 3x, I get a positive 9x. We put this expression around parentheses, and we subtract. And so negative 3x squared with positive 3x squared cancels out, and so we get 0. When you combine 11x with minus 9x, we get 2x. And all we have to do is, again, bring down the next term, which is a minus 6. We clean this up, and we repeat again for one last time. And so again, the question that you have to ask yourself is, what's missing from x that's preventing it from looking like 2x? And so in this case, the answer is just a 2. So x times 2 is 2x, and negative 3 times 2 is negative 6. We put parentheses around this expression, and we subtract. And we get that the final remainder is 0. And so from the remainder theorem, we've shown that x minus 3 is a factor of our function f of x. Again, you don't simply use the remainder theorem to show that an expression is a factor of a function. You'll have a much easier time using the factor theorem. But again, the more powerful insight or the more powerful property comes when we can use the property for the remainder theorem. Since the remainder was equal to 0, by the remainder property, x minus 3 is a factor of f of x, and f of x can be rewritten and takes on the following form. F of x is equal to x minus 3 times x squared minus 3x plus 2. So I'll go ahead and see you guys later for my next video, which is going to be on the rational zeros theorem for polynomials. Until then, take care and happy studying.